We can see your slides and video.
Yeah. Okay. Sorry. I'm gonna let the subtitle thingies go because I think those sometimes help people who are not native speakers, and since this will be recorded, okay. All right, so I'm going to talk about developing for ARM platforms with NVIDIA software tools, because that's what I said I do. That's my day job at NVIDIA is actually ARM related. We have a lot of people who work on GPUs, but I work on ARM primarily. So I'm going to tell you some pretty straightforward stuff that I hope is interesting that it exists. Just what our tools are, what they have in them, and I'm going to give you a couple of demos that I think are cool. There's other demos out there. There's other material. I've talked about NWChem in more detail in 2 or 3 other places. Since the summer, you can find that stuff. It's on YouTube already, and all the code's on GitHub. So if you don't like my data, you can make your own. But I thought it was enough to get things started, and then hopefully there'll be a couple of minutes, and you can throw tomatoes at me. Okay, go to the slide. Okay, so the NVIDIA HPC dev kit or software development kit. This is the greatly expanded and improved thing that you would normally, 3 years ago have thought of as the PGI compilers, but it's more than that. So yes, it includes the compilers that descended from the PGI compilers, and they have a lot of the same features and then more stuff. We also ship the CUDA SDK because some people just like to only install one thing once, and it ensures a lot of version compatibility, so that basically the only thing you need to get right is your CUDA driver, and then you install the HPC SDK and you're done. You don't have to play around with installing CUDA separately. We also ship a whole bunch of libraries. These are obviously all the CUDA libraries, but we also ship from in the HPC SDK a version of Openmp built correctly for all the CPUs that are obviously being used with it. And that's not super interesting. Obviously, we already heard about Bliss. If you want BLAS libraries for ARM, they're not super hard to get. And if you want them for Power, you can get them. You want them for x86, you can get them. But we ship it just to make sure that there's no excuse for anybody to compile netlib from source or use a BLAS library that gets 30 megaflops or whatever the worst case scenario is. So there's all this stuff in there. There's obviously the GPU libraries. And then there's communication libraries, the ComStack with NVIDIA and Nickel and the like. So we ship all this stuff together. Some people, they complain at me and they say, that thing is like 8 gigabytes and that makes me sad. And then other people say, it's awesome that I only have to download one 8 gigabyte thing and then I'm done. And some people complain that we release 7 to 8 times a year. And then other people are really happy that we do 7 to 8 bug fix releases a year or more. So, you can't make everybody happy all the time. So, just know that the way we're doing it is intentional. We tried to make a lot of people happy. And yeah, maybe if there's room to be improved, let us know. We also ship this stuff. So you download this as a tarball or as an apt in a YUM package, or you can get it in containers. I don't use containers. I don't know anything about containers. So if you're a container person, I'm the wrong person to ask. All right, so that's the whole bag of tricks, and I'm going to talk about the stuff that I think is cool, which is direct programming. I think everybody in the world knows about CUDA by now, so I'm not going to say anything about CUDA. And a lot of people know about OpenACC and Openmp. What you may not know, because we only released it in the very end of 2020. And I know the last year and a half have been quite boring. Nobody's had anything else to distract them, so they followed every single programming development in the last year. But we now support Openmp as well as OpenACC. Openmp is new for us, and it's not as mature. There's some things about it we don't like, but we support it anyways. And we try to deliver the best performance that we can. In general, you'll find that OpenACC is still a lot better. But if you insist on using OpenMP, then we have a pretty good implementation of it. And given that we have some pretty nice hardware, a pretty good implementation on some pretty good hardware is a nice thing. And I've got some nice results with it, where I don't see any difference between OpenACC and OpenMP. It took me a lot more work to make the OpenMP do the right thing. But the performance is the same in the end. Finally, the thing that I think that people should pay more attention to if they haven't seen it at all, we have added something called, are you still hearing me, John? My internet's complete.
Yeah, you're breaking up a little bit there, Jeff, but I think we're hearing you just fine. You keep going.
Okay, I'm gonna kill subtitles because it seems to be sending too many bytes off to the Azure cloud or however that's doing. Is it clearer now?
It's much better now.
Okay, sorry about that. I got a new antenna for my internet, but I haven't had a chance to. Anyways, so the new thing that we've done in last year is called standard parallelism. And so this includes both C++ and Fortran. So if you are following the latest specs, you know that C++17 added all of these parallel execution policies that work on the standard library methods like transform, for each, etc. And there's also something in Fortran called do concurrent. Do concurrent is pretty much a parallel loop, although there's some language lawyering that goes into what exactly that means. But in our compiler, a do concurrent loop behaves like an OpenACC loop, and that means you can nest them, and the compiler will do pretty much the same thing. So I'm going to show some examples of this stuff. If you're following GTC, I actually have my GTC talk tomorrow morning, or whenever it is for you all. It's 10 a.m. my time, which is the middle of the night for some of you. Is going to compare and contrast these in a bit more detail. But I'm going to show why I think this stuff is cool, and I'll show you some ARM numbers because, of course, that's why we're here. So this is Lulesh. You can read about it. We have a blog. The code for this is on GitHub, so you can go do this at home if you don't believe me. The OpenMP is not super awesome because they're doing a bit of a MapReduce pattern, and they have to throw in some thread IDs to get the reductions. Maybe there's something in OpenMP5 that has an even fancier way of doing this that I haven't seen. But the nice thing is there's a perfect match in C++17 called transform reduce. So, this is a nice condensation of the code. So what happens with the performance, we'll see. So these are the numbers. So this is, I download this GitHub thing, and then I edit the makefile and I run it on all my gear. So that's what you're seeing. No hidden code. And so you see here, I've got an Ampere Altra Q80 30, which is what I have in the lab, and AMD Rome 7742 64 core part, and then A100s hanging off of both of them. So the first thing is on the C++ side, this is the exact same C++ code. The only thing that changes between the A100 number and the Q80 number is the compiler flag. You either say many or multi-core or GPU. That's it. That's the only change. Compiler only. And then there's an OpenMP version, which in this case doesn't run as fast. That's not always the case, but I think in this scenario, the OpenMP isn't perfectly optimal, and that's why it's losing. But the other thing you can see here is that the ARM numbers are better than the x86 numbers. That's because, as best I can tell, ARM is better at driving the bandwidth. If you read the AnandTech post on Ampere Q80, you can see their stream numbers look really good compared to out there. So Lulu is good because A100's got HBM stacks. The other thing I'll note is you can the C++ code here. It is amazing that you can get the same, or get that performance boost from a GPU without changing the code. I have to be fully disclosing and say that number is nowhere near what the CUDA number is. So if you really want to max this thing out, you would write CUDA, but not everybody wants to write CUDA for every possible algorithm. So this is just an example of using standard language parallelism for portability and getting a very nice performance boost. There is still more performance to be obtained. And we hope that we'll be able to get more and more higher fraction of CUDA performance in C++ standard parallelism in the future with some of the new language features that are coming down the line that my colleague Bryce Edelstein-Lelbach talks about a lot. So these are the numbers. There's more numbers that could be run. You can go try it at home. I will say the reason I don't have a GCC standard parallel number on ARM is because there's something wonky in GCC standard parallelism. It works just fine in a lot of cases, but I need to go debug that. So I didn't want to show a bogus number. So it's not there. So the next thing, start with the code. This is from NWChem. This is a very PowerPointified version of NWChem, but this is, other than the syntactic perturbation for your benefit, this is what is being run. There's a full repo with all the code. You can check it all out. It's a standalone driver. You don't have to build all of NWChem to see this stuff. This is just a kernel experiment. But these are tensor contractions. So the first thing here I'm going to show is Openmp Cpu. In this case, it's x86 because I didn't have time to rerun it before this talk. And then do concurrent, OpenACC, and OpenMP all on the GPU, all with our compiler. So the first thing here is, as you might expect, a bandwidth or flop bound computation with ample parallelism will run better on an A100 than any CPU out there. That's not a surprise. The other thing here you can see is if you look at the GPU code, they're all about the same. And this is good because you shouldn't have to choose between different standard models based upon performance. They should just all work well. And so if you want to write Fortran 2008 and not think about directives, you can do that. If you want to write OpenACC and know that it won't, Intel will never support that, well, you can do that. If you want to write OpenMP and have it work with a whole bunch of compilers, you could do that. It took me a lot more work to get the OpenMP to behave in this case because I was starting with something that was optimized for a different compiler, but you can get there. I will also say that the performance portability here is never perfect. It never is, other than memcopy or DAXB. That's about the only performance portable thing out there. But you can make all of these things performance portable just by understanding that if you write Fortran standard parallelism on a CPU, you need to make it look like OpenMP would for the same algorithm. And so you can just change the parallelism around. So you get portability. The performance isn't perfect. It's within a factor of 2. So that's a really nice thing to have in a standard language, is within a factor of 2 of optimal. However, these are all compiled Fortran codes that I wrote without doing any architectural magic, and I don't have a lot of architectural brain magic the way some of my GPU optimizing colleagues do. So I will also share the number with CU Tensor. I share this because I think CU Tensor is underappreciated. It's been around for a couple of years. It hasn't really gotten mainstream adoption in the codes that it was originally created for, quantum chemistry codes like NWChem. It has been adopted in our Python and our Fortran backends for some stuff that I'll show later on the Fortran side, but also in like NumPy. So you can access it and it's really powerful, but nobody's really using quantum chemistry codes. And I thought I'd show this. So you can get 4 teraflops out of CU Tensor. So this is like a BLAS library, except it does the tensor operations with all the transposes folded in directly. And that was also mentioned in the Bliss talk. So if you know the T-Bliss thing that was mentioned by Devin Matthews, that's sort of the closest thing on the CPU side to what CU Tensor does. So that's a native tensor contraction library, and these are really cool things to have. So I thought I'd share that. That this stuff works. You can catch the code on my GitHub. The other thing, we wanted to make ISO Fortran work well on GPUs, and it does. So the thing on the left, don't ever write that. No one in their right mind will ever write triple loop dgem, and expect compilers to turn it into code. Although I've heard of some very interesting physicists who actually do this. But the point here is that the matmul intrinsic, which is doing what you see on the left, it's part of Fortran, it's been in there since Fortran 90. You can make that run on a GPU. And you say, well, why would I do that? I can just call cuBLAS or whatever. Yes, you can. You can call cuBLAS or you can call BLAS and get it to map to the GPU with compiler pattern recognition. You could do a lot of this stuff. But, for people out there that want to write real Fortran, by the standard without all the externalities and without any really old stuff, you can write this, and it looks a lot like Python. It's pretty code. And so this is just a full list of, actually it's not a full list, but it's an almost full list of all the things that we support on GPUs. And the way we support this is actually with CU Tensor. So if you write code that uses reshape and matmul and all this fun stuff, it will actually map that onto a CU Tensor backend. So you'll get pretty good performance out of that. The performance you lose will come from the overhead of obviously wrapping these things up and not having all the asynchronous support. But it's really quite amazing that you could write very textbook linear algebra algorithms, pull it out of Golub and Van Loan and write it in Fortran intrinsics and know that it'll run at multiple teraflops on a GPU. So just to wrap up, I know everybody in the supercomputing world thinks about big servers. They track the Grace announcement. They might be interested in A64FX. Those are all cool. But Linux Arch 64 is a big world, and I will say our compilers support all the things I'm showing you. And I know that because I have the right-hand three things in my basement right now, and I run our compilers on them on a regular basis. I build NWChem with them because I like that. We also have the ARM dev kit that folks may have heard about, which has an Ampere Altra chip in it, an A100. I will also emphasize for any of you who participated in the hackathon this summer, there was one issue with our compilers with Amazon Linux. So we fixed that. It'll be fixed in the next release. So it worked. Our compilers worked, but there was some glibc fun that people, if you were there, you will remember. So that's been cleaned up. We now support Amazon Linux in our compilers. So if you're a big Graviton fan, if you have a big credit card account with AWS and you want to use good compilers for ARM, you can absolutely use our stuff there. I will of course emphasize we still support x86 and we still support Power. So one of the advantages of our compilers going from ARM to x86 and back is it's the same compiler. The only flags you would have to pay attention to are CPU architecture flags. You don't have to worry about switching whole compiler tool chains, and that's kind of cool. So yeah, the talk's over, and I hope it came through with reasonable fidelity. And then I hope people can ask questions.
Awesome, thanks, Jeff. So we have about 5 minutes for questions. So take it away. Just please unmute yourself. Or type in the chat. Either way.
I have a quick question. Thanks, Jeff. That's a really interesting talk. So I guess the idea is that do you think like more of these like parallel features, as they get introduced into like future versions of C++, are we going to move more towards this not totally performance portable, but like this world of just trying to use the C++ parallel abstractions, rather than like an Openmp or OpenACC to get good performance across platforms?
So we're certainly optimistic. I think what it really comes down to is choice. So HPC folks are really comfortable with directives and pragmas. There is a whole world out there of people who just hate those things. The sort of real purist C++ programmers think that pragmas are just absolutely horrible. You have a lot of people in the AI world who don't like them. I don't know all the reasons. And if you look at like an Apple platform, so Apple Clang doesn't support Openmp. I don't know why, other than they just don't care, and they didn't want to bother doing it. But you can obviously run Openmp on a Mac. You would just have to get the homebrew compilers. But I definitely am able to use standard parallelism on a Mac. I can't remember which compiler. It might have been homebrew GCC, in which case it's who knows what Apple Clang will do. But I think it really comes down to, if people want to use just the language, then they can do it, and they can reason about it from the standpoint of just that language. If you know anything about Openmp interaction between the base language and the pragmas and directives for like things like atomics, it's really hard to reason about what happens before mean when you have Openmp threads and language atomics, or P threads and Openmp atomics, all sorts of things like that. And I think it's just cleaner to build everything together. The other element for us is, CUDA is increasingly a modern C++ dialect, and we have a lot of people that like CUDA and are going to use CUDA, even though it obviously supports only one platform, to get max performance. And what we'd really like is there to be a nice continuum between modern C++ in CUDA and modern C++ that's CUDA agnostic. And if we have standard parallel features, people can start out writing standard parallelism, and then they can bolt on as much CUDA as they like later, but they can start from a reference point that's highly parallel code and hopefully asynchronous code, rather than trying to take sequential code and go to CUDA. Because then, then you end up in a situation where it's like super fast, or, it's correct, but super slow. And so we sort of want to see more parallelism everywhere. And actually, part of this is in my GTC talk of trying to say, here's where you would use standard parallelism and not use CUDA, and then of course where that's going to be a bad deal.
Jeff, I was actually going to ask the very similar question. So, I mean, what is NVIDIA's opinion on converging CUDA with C++ or modern C++? Right. I mean, at what point does CUDA, basically just become a future C++ standard feature, right, with the parallel features, right? I mean, could you see those converging at some point in, say, 10 years?
No, maybe that's not the answer people want to hear, but I'll tell you why the answer is no. The abstract machine model for C and C++ is, as you know, right, a PDP-11 or something like that. And C++ doesn't have a way to reason about language features for things as simple as NUMA. And so there isn't really a way to build in all of CUDA into C++, because C++, I mean, obviously everyone who's working on C++ understands what CUDA is. But if you go to the language, the book, and you say, how would I add, shared local memory here? There is no concept by which you could do that. They're just, the abstract machine says, I don't know what you're talking about. So I think CUDA will always have things that are not in the ISO standard language. What we'd really like to see, though, is all of the concepts from CUDA that are expressible in C++, they would be, because those are, things like having a lot of threads. That's obviously a portable concept. An atomic memory model, that's a portable concept. Those are things that have already gone in. The thing that standard parallelism lacks today, which is a huge issue, is asynchrony. So not the asynchrony of like hanging off of an async statement, but of the ability that you would actually have an executor that operates asynchronously, and that you would exploit that concept. And that concept, of course, has been in GPU programming for years. It's always been asynchronous kernels by design, because that's a good thing. And so what C++ 23 senders and receivers give us is a way to express that asynchronous kernel launch in a standard way. And I think that'll be a huge step forward for everybody who's got an asynchronous execution engine, whether it's, I don't know what Apple's execution model is for AMX, but you can imagine an on-die async accelerator or an off-die async accelerator both being something that you could hit with that feature. And so we really want to see that. I will also say, as you know, right, standards are designed by committee and they take a long time. CUDA is designed in collaboration between the CUDA architects on the software side and the hardware architects at NVIDIA, and they move very, very quickly. So CUDA will always have features in it that couldn't possibly be standardized because we can't possibly communicate that information to the ISO committee in time to let them, ruminate on it. So I don't see CUDA becoming part of ISO. What I see is that a trickle-down effect of the things in CUDA that become truly normative in programming become part of ISO C++, so that we can spend more time on doing, really crazy new and interesting things in CUDA that we don't even know how to bring into ISO C++ yet.
Awesome. Thanks for your talk, Jeff. We're out of time, unfortunately. We got to hop to the next speaker.